Sparkling drinks are just dandy, the chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves a treat.
And we're back. I hope you got yourself a tasty treat. Right. I think that's it. So let's see what happens when we increase the rate of predator growth relative to rabbits. So what happens when you get more predators per rabbit? So we can bump this number up a little bit, and you can see that this one's actually rather intuitive. You can see that the number of prey is going down and the number of predators is going up. It's also true that the length of the cycle is getting longer. And these lines are the lines where we started. Right, so that's what happens when you increase how fast the predators grow based on the number of rabbits. The number of rabbits goes down, but the number of predators goes up. So let's reset that. Similarly, if we say that you don't get that the ratio of how fast predators get, you get more predators based on how many rabbits are. If we make that smaller, well, the rabbits go up, and the predators don't really go up much at all. So this variable control has strong control over how many rabbits there actually are. All right, so faster predator. So, okay, we did that one. So what if we increase, I think this is the one. What if we shorten predator fractional decrease rate? I believe this is the lifetime. So if we, so this variable controls how essentially how long predators live, and if we make that smaller, predators live it actually controls how long they how quickly they die. So if we make them if we make the rate at which they die smaller, they live longer. Again, we have some impact on the rabbit population, but also note how the length of the cycle gets longer. I should have called out earlier, but also we can see these changes down here in the phase space. There are some states, particularly in the low numbers, that are like our base case, but there are also cases we can also get to regions in the phase space that we can't get to with other sets of parameters. At some point, well, here the rabbits have gone extinct, so that's not so good. So back to where we were. If we increase this, that is, if we say the predators die more quickly, the number of rabbits gets bigger, but the cycle goes much faster. Right, and again, you can see note down here how this figure is called the attractor, and the attractor is the graph, the map of all possible states. So An attractor is a graph in phase space. It's a set of points in a given phase space. Oh, let's see, how do we get back? We move the attractor back toward the initial case. All right, a couple more here. So what if we increase the rate at which rabbits reproduce? Now, rather than moving the base away, we're really just expanding we're expanding the attractor. The total number of rabbits goes up. The total number of predators goes up. It's hard to say what's happening with the cycle. The cycle time looks like it's about the same. And then, similarly, if the birth rate of rabbits goes down, then the number of rabbits goes down. The variation in the predators nearly goes away, and we can see that by this width here. So the difference between the maximum number of predators, the maximum number of predators at any given time with a set of parameters is this width, and the maximum variation in prey is this width. All right, so we've had rabbits get better and better. Let's say this one is weird. Let's say that the predation rate goes up. That is, predators eat more rabbits. The number of rabbits goes down, but the number of predators goes down as well, and that's because as the rabbits go down, we have a negative feedback in here. And then similarly, if it goes up, things can explode. So if the predators need only a small number of rabbits in order to carry on, things get quite exciting. We can blow things right out of the park. We might expect that other limits would kick in before that happens. All right, so that's those parts. I'm going to reset the model. Here we go. All right, so we're back to where we were. Now, we've seen that the phase space changes depending on the parameters here, and we varied them one at a time. And so I want to do two things. One, let's do an example where, let's say this set of parameters has been stable for a long time. But let's say there is some climatic or an external environmental disturbance happens, and the starting place. So this is at time 0. There are 10 predators and 100 rabbits. Let's change those numbers. Let's say there are 150 rabbits and 15, so the ratio is still the same, 15 predators. You can see that the rough shape of this stays the same, so the ratio of these, but the variance has expanded dramatically. So now, if we let's say we decrease, based on this, decrease the reproduction rate of the rabbits, we don't get back to, we can get close to our base case, but we don't ever quite swing through it. Well, let's say, well, what if we then adjust the predation rate? Can we get closer? And the point here is that you could probably diddle these things so that they got close, but that for any given set of parameters here, the attractor is going to be unique. It's going to be unique. And that the initial conditions, let's go back, let's reset here, that the initial conditions matter a lot. So if we have, say we have, for our 100 reference prey, we have 25 starting predators, very different attractor. And the reason I'm calling this out is you could imagine that the system could get reset by a big storm that kills. Well, I've done it the other way around. Let's let's do a death scenario here. So 10. This is where we start. But let's say a storm results in losing half of the predators. The attractor becomes very different. Similarly, if a storm or some event caused us to lose half of our rabbits, starting rabbits, the attractor is again very different. So the phase space and the attractor contain a huge amount of information about the behavior of a given system. And you can tell whether two systems are, you can tell a lot about a system by looking at its attractor. In particular, attractors that do this, that have this looping thing, they're going to have these kinds of cyclic behavior. All right, I'm going to wrap that up for now, and we'll come back to this with some other applications going forward.